So we're asked to find the graph of this function, and we have to do it completely without any technology. So the purpose is to use calculus in order to find where the function is increasing and decreasing. We can use the first derivative test, therefore, to find max and mins. And then we'll repeat the same process with the second derivative to find inflection points and where the function is concave up and concave down. So to begin, I need to find the derivative. And when I look at this, I either can go directly to product rule, or as you guys know, I like to use algebra whenever possible. So I would see this as y equals, so x to the 5/3 times x squared. So I'm thinking of this squared as 6/3. So I add 5/3 plus 6/3, I get x to the 11/3 minus, when I distribute, 3x to the 5/3. Okay, now I have to take the derivative. So again, don't convince yourself just because you did some algebra here that you've done calculus. We haven't taken the derivative yet. But so now the derivative just requires power rule. When I subtract 1 from 11/3, I'm going to get, or subtract 3/3 from 11/3, I'm going to get 8/3. And then when I pull down the 5/3 times the 3, I'm just going to get 5x to the 2/3. So there's my derivative. And so what I want to know is, where is this derivative either 0 or undefined? Now, this function's never going to be undefined because I don't have any denominator, I don't have any negative exponents or anything like that. So I really just want to know, where is this equal to 0? And in order to do that, I have something sort of unusual compared to most of the other problems we've been working with, because we have all these fractions. What I'd like to do is factor. That's my usual approach, is to factor. So I want to think about what is the biggest thing I can factor out of both of these. So it's not an integer exponent, but I can factor out x to the 2/3 out of both of these terms. And I would be left with 11/3 x to the, if I take 2/3 out of this, I obviously am left with 6/3, so that's where I'm getting my squared left, and then minus 5. So now that it's factored and I have it set equal to 0, I see that by zero product property, either x to the 2/3 equals 0, or 11/3 x squared minus 5 equals 0. Now it becomes a little bit more typical. Here I can solve x is 0. Here I've got a quadratic, so adding 5 to both sides, and then multiplying both sides by 3/11 to get rid of that coefficient. I've got 15/11 equals x squared. So x equals plus or minus the square root of 15/11. Or if you like, the decimal equivalent. But actually I like the exact value here, because I feel like Desmos or a graphing calculator is going to approximate things with the decimal. And I always like to see that I have a little bit more it gives me a feeling of empowerment to feel like I know how to do this even better than the Desmos is going to give it to me. I'm going to give it to me and get it as an exact answer. Okay, but now we want to apply the first derivative test. And the first derivative test tells us that these two critical values break the domain into 3 intervals. Now on those intervals, we know the function is going to be monotonic, so I just need to pick a particular test point. So say I pick y prime of -10 or something like that, and if I check what its value is, it's actually going to be positive. And you may have picked a different test value, but regardless, we all would get a positive result, and so we know the function is increasing on this interval. And I'm realizing I forgot my critical value 0, so let me fix that. Okay, there we go. So I'm sorry, I need to correct myself. So we had 1, 2, 3 critical values. That breaks the domain into 4 intervals. Okay, so for time purposes, I'm going to just tell you that what the results are here. But even though I just filled that in for you, you're going to be sort of fooling yourself if you just let me get away with that without double checking yourself. So you should be checking a test value in each of these 4 intervals, because when it comes time for the test, of course, you have to do it on your own. Okay, now using the first derivative test, we see we have a function that's going from increasing to decreasing. So that's telling me that we have a local max maximum at negative square root of 15/11. And again, you could use the decimal if you prefer, comma something. We have to go back to that. And then there's no other place where I'm going from increasing to decreasing, but I've got a local minimum where I'm switching from decreasing to increasing. So that would be a positive square root of 15/11, comma something. To find the something, I'm always going back to the original function y and substituting that value in to see what I get. For that purpose, I'm going to just go ahead and round that, so 2.119, and for the minimum, negative 2.119. Okay, now hopefully you have a little bit more space left over than I do writing with this big electronic version of a pen. So I want to keep track of this information here, but I now need to repeat this whole process all over again, except instead of for the first derivative, I'm going to be doing it for the second derivative. Now this isn't the second derivative test. Remember, the second derivative test is an alternative way to find the local max and mins, although it's inconclusive in one case, but it's basically a concavity test. Okay, so we're going to find the second derivative, make a table to see where the function is changing concavity to identify inflection points. So I'm going to erase to make some space. Okay, so back to my first derivative. Now if I want to take the second derivative, it's again power rule. So I get a function that has a positive exponent and a negative exponent. So this is my key right here, that this function is going to be undefined somewhere. And so I want to write it as a fraction, try to get a common denominator so I can find where the derivative is both 0 and undefined. So my common denominator is going to be 9x to the 1/3. So I need to multiply this fraction by x to the 1/3 over x to the 1/3. And this fraction I'm going to multiply by 3/3. Combining them as a single fraction, here we go. And so now if I want to know where the second derivative is 0, I'm really solving for where 88x squared minus 30 equals 0. Or out of lack of space, I'm going to just squish that. So dividing both sides by 88, we're looking at where x squared equals, reducing the fraction, 55/44. So we're looking at plus or minus the square root of 15/44. And then where the denominator is 0 is where 9x to the 1/3 equals 0. That's where the function's derivative, or second derivative, is going to be undefined. So here is where y double prime is undefined. And for these two values, y prime is going to be 0. Y double prime, sorry, is equal to 0. So now we repeat with these 3, 1, 2, this time I'm going to actually catch them all, these 3 critical values. Sorry, they're not critical values anymore, officially, that's not the word. But these are 3 values that breaks the domain up into 4 intervals. On those intervals, the function's concavity is fixed. So let's set up a table again. Okay, so pardon my handwriting, but there we go. So what we're going to do now is check the second derivative for some test point. Again, I mean, it doesn't matter which value we pick, but we all would get the same sign. So this one's negative. So again, please don't just leave this up for me to do. That's not helping you at all prepare for the exam. So pick some value between negative infinity to negative, whatever the square root of 15/44 is. Pick some test value, evaluate that at the second derivative. So plug that in for x everywhere in the second derivative. And you can use either this version over here of the second derivative or this version or anything along the way. But substitute the value in and you'll see you'll get a negative result. And that's telling me that the function is concave down. Okay, I'm going to pause the video to fill out the chart, and I would encourage you to pause the video to try these test values yourself. And so we see we have changes of concavity at, in fact, from concave down to concave up, and then again from up to down, and then again from down to up. So we have 3 inflection points. And again, for these inflection points, we know the x values, but to find the y values that correspond with it, we're going to plug those back into the original function. We're not looking for, I mean, we know if we plug it back into the second derivative, we're just going to get 0 or undefined, right? So the point is, what are these points on the original function? Okay, so here's our inflection points, and let's put this all together to graph. Okay, after plotting the 5 points that we have here, we have something roughly like this, and you'll forgive my not so nice handwriting with this. And now you should have both the first derivative test still pictured and you have the concavity test. So I don't have all the screen for that, so you're going to have to sort of flip back. But for values all the way up to negative square root of 15/11, the first derivative test said the function was increasing. And this concavity test tells us it's concave down. So I need to graph something that's increasing and concave down up until this point. So it's going to look something like this, and it's just going to head off in that direction. So increasing and concave down. And I'll write that, increasing, concave down. Now I look between my next 2 points. I've got, so now I'm between negative square root of 15/11 and negative square root of 15/44. So again, refer back to the first derivative test. That's going to be telling me that I'm decreasing, but I'm still in this first column. So I'm in the second column for the first derivative test, but I'm still in this first column for the concavity test. So I'm still concave down. So decreasing and concave down. And so that's going to look kind of like this. And now I look between my next interval, between this and 0. And so again, I'm just reading off of both those charts. So for the first derivative test, I'm still in that second column. So I'm still decreasing, right? Because I'm going all the way up till 0. But for the concavity, I keep almost saying second derivative test. For the concavity test, now I'm finally in the second column because I'm between negative square root of 15 over 44 and 0, right? So that's this column. So that means I'm concave up now. So decreasing and concave up. Oops, I missed my dot. Pretend that's connected. And we just continue like this. So but in my next interval, I'm still decreasing. But now I am concave down. So decreasing, concave down. And then in the next interval, I am going to be still decreasing, but concave up. Make sure you're understanding how I'm getting all these pieces. And then from this point on, and the first derivative test tells me I'm increasing, but I'm also concave up by the concavity test. So now it's going to be going off like this. Okay, and double checking on Desmos, we see we can hover here, and here is our local maximum at negative square root of 15/11. And again, notice that Desmos is giving us a decimal approximation for this. It's also giving us this inflection point 0, 0, and it's giving us the local minimum. But it's not recognizing the inflection points happening here, right? So here we see the function's concave down, and it is switching to concave up, but it's not recognizing the inflection point. So again, I want to give you this sense of empowerment that you now can come up with a better graph or more information on this graph, exact values if you need them, inflection points, all without calculus. I mean, I'm sorry, all without technology, but with calculus.